In this presentation, I would like to discuss some examples which will make the concept of graphical method of drawing shear force and bending moment diagram more clear. Let us discuss this example whose shear force and bending moment equations we derived. We will now try to draw shear force and bending moment diagram using the graphical method. So this is a overhanging beam given to us. The beam is supported at point A and C. The span between point A and C is 10 meter. The beam has got a 4-meter overhang, and at point D of the overhang, we have 30 kilonewton applied. Within the span, the beam has a uniformly distributed load of 20 kilonewton per meter applied partially at 5-meter span. Now, as discussed, first of all, we have to determine the reactions. So the reactions at A and C comes out to be 63 kilonewton and 67 kilonewton respectively. Now, let us try to draw the shear force diagram. Whilst drawing the shear force diagram, we will use the four expressions which we derived. That is, the magnitude of the applied load is equal to the slope of the shear diagram, dV by dx. The shear at a point is equal to the slope of the moment diagram, dm by dx. The change of shear between any 2 points is equal to area of the load. And finally, the change in moment between 2 points is equal to area of the shear force diagram between the 2 points. Our sign convention will be the same as discussed previously. Thus, the loads which are facing up will be positive. The positive shear at the left portion of the beam would be facing down, and the positive moment at the left portion of the beam will be in the counterclockwise direction. So the shear force diagram will start right at point A as per our convention. At point A, there is a reaction of 63 kilonewton. Now we have to ask ourselves that whether the shear force would be above the reference axis or below the reference axis. Above reference axis would mean that the shear force is positive, and below the reference axis would mean that the shear force is negative. If our reaction is facing up, i.e. positive, then at a very small infinitesimal distance at right hand side of this point, we would have the positive V facing down, and using summation of Fy equal to 0 would make this V positive. This is something which we already discussed whilst deriving the shear equations. So we have to work out the sense of shear at the first point by making summation of Fy equal to 0. We check whether the reaction is in a positive sense or in the negative sense. And then at a very small infinitesimal distance at right hand side, we apply our reference positive shear and then equate this equation equal to 0. So 63 minus V would be equal to 0, and that gives us shear equal to 63 kilonewton. If we are not able to do this exercise in our mind, then we won't be able to start our shear force diagram. So once we start it, then the rest of the shear force will follow using the four expressions which we discussed. So 63 kilonewton is positive. Now we check the segment AB, which has got UDL applied in the negative Y direction. From the point 63, either we can go up or we can go down. In this case, we will go down because the UDL is opposing the direction of the reaction. Please remember, shear force is summation of Fy equal to 0 to the left of the beam. So R1, which is 63 kilonewton, minus 20 times 5, which is 100 kilonewton, will give us minus 37 kilonewton. So the shear at the boundary B of the segment AB will be minus 37 kilonewton. This clearly tells us that the shear force is incrementally reducing. So initially it's positive and then it becomes negative. Another question which we might ask ourselves would be that what sort of curve should join A with B? What should be the degree of the curve? Since the UDL is 0 degree, thus the shear would be 1 degree up, that is 1 degree. Therefore, we would have a straight line having some slope. Looking at the shear force diagram of segment AB, it is clear that the shear is changing from positive to negative. Thus, there would be a point where the shear is 0. This point can be easily determined by equating the reaction, which is 63 kilonewton, with that portion of the UDL, which will make it 0. So R1 63 minus 20 times X should be equal to 0. So X define that length which will make the reaction equal to 0, and X will be equal to 3.15. X is equal to 3.15 is now worked out. So we have now determined all the unknowns in the shear force diagram with respect to segment AB. Now let us move to segment BC. First of all, in the BC, we see that there is no external load. Please note that for drawing bending moment and shear force diagram, the external loads are the applied loads and the reactions. So segment BC has got no load. That means to say that the shear force will be 1 degree up, which is 0. So we have a 0 degree curve for segment BC. In segment CD, again, we don't have any load within the span. However, at point C, there is a concentrated load acting. As we discussed, concentrated load is a cause of discontinuity and it causes jumps. So minus 37, which is constant throughout the BC, will be added to 67, keeping in mind that 67 is having a positive direction, and we will get 30 kilonewton shear at the same point. So due to the reaction 67 kilonewton at point C, we have two shear forces. This is in accordance with this expression, which is the change in shear between the 2 points is equal to the area of the load between those 2 points. Thus, we have the load applied only at point C. We can take V2 minus V1, which is 30 minus 37. That makes 30 plus 37, and that equals R2, which is 67 kilonewton. So the equation V2 minus V1 is equal to area of the load is satisfied. In the segment CD, then we have no load within the span. So 30 kilonewton is constant throughout the CD. After that, this 30 kilonewton is brought to 0 by the applied external load, which is in the opposite direction. Thus, our shear force diagram is closed. Please remember that if the shear force diagram doesn't close in the end, that means that we have made some mistake in the calculations. In the shear force diagram, there will always be a jump at the point of concentrated load that is coming in the middle of the span. So if we had a concentrated load applied somewhere in the middle of BC, then we would have seen a jump similar to this one in between BC, and both values at the jump would have added to the load applied at that point. After this, we will draw the bending moment diagram. First thing to appreciate is that the bending moment diagram will be 1 degree up to the shear force diagram. So between AB, the bending moment diagram would be of 2nd degree. In other words, it would be parabolic. Since A is a simple support, therefore the bending moment diagram should start from 0. As we discussed, if the shear between any two reactions is 0, then at that point we would have a maximum moment. So at the point of 0 shear, we would expect maximum moment. This maximum moment magnitude will be equal to the area of the shear force diagram. We have already discussed this in the equation M2 minus M1 is equal to area of shear. So 99.23 minus 0 would be equal to area of this shear force diagram, which is named as A1. A1 would be equal to half 3.15 into 63, and that will give us 99.23 kilonewton meter. Now we have to ask ourselves that how should we join point A to the point of maximum moment? Should it be joined by a convex curve or a concave curve? The convex curve has got a finite slope at the starting point, and it becomes zero at the point of maximum moment. A concave curve would be starting from zero slope and will adopt a finite slope at the point of maximum moment. Since at point A we have a finite value of shear, therefore the moment at point A should have finite slope. Thus, we should adopt the convex curve. Similarly, at x is equal to 3.15 meter, we have zero shear, and in the bending moment diagram, we should have zero slope. So the convex curve fits well with the expressions which we derive. In order to find out the moment at the boundary B of AB segment, we will add area A2 to the maximum moment. A2 would be equal to minus half 37 into the length 5 minus 3.15. Please make sure that we are particular about the sense of the areas. It is clear from the bending moment diagram that after reaching maximum, the moment will start decreasing. We can also find out moment at a particular point within the beam by using the moment equation, which is summation of moment to the left. So in order to find out moment at x is equal to 3.15, we can take R1 into 3.15 minus 20 into 3.15 into 3.15 by 2 plus m equal to 0. That will give us the moment 99.23. Similarly, we can find out moment at point B. So there are two ways of finding moments, either from shear force diagram or from the first principle using the equation. After segment AB, we will move to segment BC, where there is no load and we have 0-degree shear force diagram. Thus, in case of moment, we would have first degree line. We will again find out the area A3, which is 37 times 5, and add that to the moment at B. We will get from there minus 120 kilonewton meter. After this, we will add the positive area A4 of segment CD, which is 30 times 4, and that will give us 120, i.e. the negative 120 and positive 120 will cancel out, and our moment at point D would be equal to 0. This makes sense because D is the free end, and at free end our shear and moments are 0. Thus, our shear force diagram and bending moment diagram have closed at the end point D. From the bending moment diagram, we can say that if our support has got the spans on both sides, then we would have same moment but in opposite direction appearing on both sides in such a way that the summation of that moment will be equal to 0. Now let us quickly run through this another example. In this example, we have got a span AE, which is made up of 4 segments. Segment AB has got a uniformly varying load of 120 pound per foot applied, and the length of AB is 9 feet. Span BC, segment BC is 1 feet long and having no external loads. Span CD has got a UDL applied in the upward direction and its length is 4 feet. segment DE is 1 feet long, and at point E we have 120-pound load applied. We have got an external load R1 240-pound applied at point A. We are asked to draw shear force and bending moment diagram for this arrangement of loading. Now again, the direction of R1 is facing up. So similar to the previous example, we have a positive shear. Since AB segment has got uniformly varying load, which is a first degree line, our shear force diagram between AB should be a second degree curve, and that curve is parabolic. At point B, this curve will give us negative shear value, and we can verify that by summing 240 with the area of the UVL, and the UVL is facing down, hence in negative direction. So if we subtract the area of UVL from R1, we would get minus 300. Now we have shear changing from positive to negative. Hence, there would be a point where the shear is zero. So that point needs to be determined. Another thing is that we have to work out whether the curve joining these boundary shears is convex or concave. Since the magnitude of load at point A is zero, that tells us that the slope of the shear force diagram should be zero, remembering that W is equal to dV by dx. So the slope of the shear force diagram at point A is zero. At B, we have a finite value of load, hence we would have a slope that is finite, and we can see that the slope is finite. So we have established the curve joining point A with point B in the case of shear force diagram. In order to find out the distance of the point having zero shear from the left support, we have to equate again the reaction with the magnitude of the UVL that will nullify the reaction. In other words, R1 minus half xy must be equal to 0. X is the distance from the left support where the shear force is 0, and y is the ordinate of the UVL at a point where the shear force is 0. We can use similarity of triangles, i.e. 120 by 9 equal to y by x, and we will get y in terms of x. Then from here we can plug back the y in the equation 240 minus half xy equal to 0, and we will get a quadratic equation. That quadratic equation, once solved, will give us x is equal to 6 feet. Correspondingly, FB will be equal to 9 minus 6, which is 3 feet. So we have found all the unknowns in the shear force diagram for the segment AB. Now we will move to segment BC. In segment BC, there is no external load applied. So we would have a 0 degree SFD. Minus 300 will stay constant in BC. In CD, we have a UDL applied which is facing up. So minus 300 will be added to the magnitude of this UDL, which is 420 pounds, i.e. 105 times 4. So 420 minus 300 gives us 120. Again, we have a change from negative shear to positive shear within the segment CD, and we would have a zero shear somewhere. Now to find out that zero shear, we will make use of similarity of triangles. So this distance A prime by 300 should be equal to 4 minus A prime by 120. From here we can find out A prime easily, and 4 minus A prime will come out to be 1.14 feet. In the segment DE, again there is no load within the span, so 120 will stay constant. At point E, there is a 120-pound load applied, which will bring this positive 120 to 0. Thus, our shear force diagram is closed. Now let us see how the bending moment diagram can be drawn. So again, at the point of 0 shears, we would have maximum moments. And the reason is that we have these shears appearing between the concentrated load. The reason I say that we would have maximum moment at zero shear provided the shear is in between the concentrated loads is that in the case of cantilever beams, the point where we have maximum shear would have probably the maximum moment. It's only in the case of simple supports that we can have a case where at the point of zero shear, we would be having maximum moment. So in order to find out this maximum moment, either we have to get the area under the curve within AF, which is challenging. We work out the moment at point F using the first principle. We already know the distance x, we just find out the moment, and that moment will be r1 times 6 minus the portion of UVL times the one third of the distance of the base. Please remember we have a triangular load, and triangular load centroid is located at one third from the maximum ordinate. So we can find out 960 kilonewton meter at point F. After that, the area of shear force diagram is negative, thus the magnitude of 960 will be reduced. Again, at point B, we can find out the moment from first principle, and we get moment 540. By first principle, I mean that we take summation of all the moments to the left and find out the resultant moment. For BC, the area is 300 times 1. So 300 times 1 is the area of shear force diagram. 300 minus 300 when added to 540, we get 240. After this, we can find out the area of this other triangle, which has got one side as a dash and another side as minus 300. So we can work out the area of this right triangle and that and add that to 240 kilonewton meter. This will take us to minus 188.4 kilonewton meter at point G. So from positive peak, we have now gone to the negative peak. After this, the shear force diagram become positive. So this positive area, which is 120 into 4 minus a prime into half, is added to minus 188.4, and we would get minus 120. After this, we have the last segment, which is DE, and its area is 120 times 1, and that when added to minus 120 will give us 0. Thus, at the point E, our bending moment diagram has closed. So the main takeaway from whatever we have discussed so far is that we can use these four expressions and draw our shear force and bending moment diagrams. Firstly, we have to draw the shear force diagram. We determine all the unknowns in shear force diagrams, especially the locations where shear forces are zero. If the shear force diagram is made up of rectangles, squares, and triangles, then the finding out area is easy. However, if the shear force diagram has got curves, parabolic or cubic curves, then it becomes more challenging. So we use first principle to determine moments if the shear force diagram has got curves higher than first degree. Finding moment by first principle means that we work out the moment based on summation of moment at the left segment would be equal to m.